Welcome back. All reactor SCRAM reset permissives are now met. With SCRAM, active control of the reactor protection and control rods is disabled. Reset SCRAM. We can now start to withdraw the reactor protection rods. Select Reactor Protection Rod 1 to retract. This will start the retraction of the protection rod 1 and will continue until either the stop button is selected or the rod reaches the fully retracted position. To ensure we do not introduce too much reactivity to the system too quickly, we must follow the startup rate gauge on the right of the page. A startup rate of 2 is the limit for safe operation. If the rate reaches 3, then the reactor will automatically trip and you can start again. This startup rate measures the increase in reactivity from one moment to the next. Once the protection rod 1 is fully retracted and everything else looks fine, we can go ahead and retract protection rod 2. It is always a good idea to be slow and sure when retracting protection and control rods, as maybe the criticality estimate is wrong and we achieve a chain reaction too early and too quickly. You will notice also the trend in the center of the page shows the number of hits per second on the neutron detector. It has started to trend upwards, which means we are heading in the right direction. With all protection rods retracted, we can now continue retracting control rods. Retract control rod 1 and stop it at the 50% position. Retract control rod 3 and stop it at the 50% position. Retract control rod 2 and stop it at the 50% position. Retract control rod 4 and stop it at the 50% position. Continue retract control rod 1 and stop it at the 25% position. Continue retract control rod 3 and stop it at the 25% position. Continue retract control rod 2 and stop it at the 25% position. Continue retract control rod 4 and stop it at the 25% position. Note that the neutron detector trend in the center of the page is really showing an upward trend. This is good. When this trend line becomes near to the top, we can expand the range. Back through each control rod in turn and retract them to the 10% position. Now drive the control rod 1 to the fully retracted position. Then move control rod 3 also to the fully retracted position. Keep an eye on the neutron detection trend. If it suddenly spikes upward off scale, then the number of neutrons emitted by the chain reaction has exponentially increased and criticality has been reached. Then control rod 2 also to the fully retracted position. Okay, we are down to the last control rod. Our estimate was that with the boron concentration we have currently, the reactor should go critical when this rod is at the 10% position. Let's pulse this rod one step at a time. Now the neutron detection trend has gone off-scale and the source range meter above it is also off-scale. Criticality has been achieved and we now have a self-sustaining chain reaction. Change to the intermediate range flux detector. Although the reactor is now critical, the power output is still very small. So we head back to the chemical and volume control system page. If we reduce the boron in the primary circuit, reactivity will increase and reactor load will go up. Put a set point of 2433 parts per million and select dosing rate to slow and engage. As we are increasing reactivity, this will show on the startup rate gauge. Remember to only dose boron or dilute at a safe rate. If rate exceeded, then stop diluting. Whilst the reactor power is very low, we still have high temperatures in the primary circuit and we are circulating this hot water through the steam generators. So each steam generator is making a small amount of steam. This steam is currently being dumped to atmosphere through each leg's power-operated relief valve. Start turbine gland steam system. Once gland steam pressure is adequate, start condenser vacuum system. Note the pressure in the condenser will rapidly decrease. In real life it takes much longer than this, but I have sped it up here. Reactor power will increase very slowly in the beginning, however rest assured that it is increasing as the startup rate gauge is indicating. We can skip forward as this may take some time. With reactor load approximately 5%, we can select the flux metering readout to power range. This consists of two gauges that measure differing properties from the reactor core. The top gauge can also be changed from an analog to a digital readout, which helps to show the slow progression of the reactor load upwards. Both these power range meters are however prone to wandering from the actual measured value due to distribution of the chain reaction within the core and other factors. They can however be calibrated online, and this should be done on a regular basis to ensure the reading is accurate. Calibration of these meters is done against the primary and secondary circuit calorific. These meters tend to be more accurate from 30 to 90% power range, but even then can drift over time. Some reactor protection is linked to these meters, so it is best that you calibrate regularly. Reactor is now in mode 1, power operation. From this point we will no longer use the startup rate gauge for ensuring a safe increase of reactivity. We will instead use the load increase rate gauge below it, which has slightly different limits. We want to continue to increase reactor power. Time to review through all the control screens again. Put a set point of 2410 parts per million. Put a set point of 2395 parts per million. We have reached our target of just over 20% reactor load. At this load we can start up the steam turbine. This will be covered in the next video. This has been a training video for the nuclear simulator application programmed by Richard Smith.